Yo, what's up, everyone? So, today I'm gonna try to explain what molar conductance is. Like, I've always struggled with this concept, I've never understood it, but I think I've developed a reasonable understanding of this topic, and to consolidate this understanding, I hope to share it with you all, that is, myself. Let's get into it. So basically, the first thing y'all gotta realize is I'm struggling to record because I'm holding it in one hand. Yeah, so basically, you got this beaker sort of thing, and like you dip some sort of metallic uh, electrodes, right? And there's like a solution, right? So the thing is, uh, you want to know its conductance, and why would you want to know it? So first let's deal with the case of metals. So you have a metal here, length L, cross section A, resistivity rho, and R is equal to rho L over A, right? And the thing is, in circuits, electronic circuits, you're concerned more about the resistance, because resistors dissipate energy and that's that sort of stuff. But when you're doing electrochemical reactions, you want to know how good it actually conducts your electricity and stuff like that. Because normal water is a conductor of electricity, but like distilled water isn't, and all of those sorts of stuff. So like in metals, you have this cool relation that gives you, and this resistivity uh, kind of is like a intrinsic property of the metal. So people would want to draw similar uh, comparisons with solutions, right? So what they did is they took this exact thing, they copied the hell out of it, and that's what they told. But they're like, oh, never mind, we don't really care about resistance, so let's take the reciprocal on either side. And you get rho, 1 over rho A by L. So, and if you notice this thing, this L by A, this is the length between them, and this is the area of cross section. And same thing, length between the two ends and area of cross section. So the thing is, this thing can be dipped in some other solution, and these two will remain constant. So it's pretty obvious that this L by A is a property of the electrodes that you've chosen. So they just gave it a fancy name as G star. Why G star? We'll get into that later. So they're like, yeah, 1 over resistance is more useful for us. And if resistance is R, 1 over R is the inverse of it, which is conductance. They gave this as G. And this 1 over rho, like rho is resistivity. So 1 over rho is conductivity. So like in so they gave the thing as kappa. Like I don't really know, they like usually in physics I would have assumed that they would have given it something like sigma or something, but they've given it kappa, and this is A by L, but we've literally named L by A as G star, so this is 1 over G star. I think the reason they named it G star is just for it to sound nice. Kappa is equal to GG star. Like it's like so easy to remember. So we got something like, this is a constant, by the way. Like it's dependent on the solution itself. But now that raises a problem actually, because resistivity over here is like perfect constant, like not a constant, it's like a, it's like perfect. It can like describe your metal's resistance beautifully, except like with variation in temperature. But kappa has like a hidden issue, you know. And the problem is, let's take the same example. Let's say this has some, okay, this is like length. Okay, so let's say that this has concentration of 1 molar. And then this one, I took the same electrodes and dipped it in this. And this has a concentration of 0.5 molar. The thing is, kappa should have ideally been a constant for this solution, like for any solution for that matter, because it's literally the reciprocal of a constant. But the thing is, intuition says that because the concentrations are different, your kappa value would also be different, and that intuition actually turns out to be right. So kappa is like, it's like secretly proportional to molarity somehow, like molarity or like concentration, whatever. So it's like secretly proportional to this thing, right? And the thing is, since it's secretly proportional to this, if we were to just divide it by concentration, then that should solve our problem, and it would be a legit constant and not be like a variable constant like how it used to behave, how it's behaving right now. So that's why this kappa by concentration, or like molar concentration, they call this as a new thing, which is molar conductivity. And the thing is, here I've written c power x. The reason I've written c power x is because honestly, I don't know why. Okay, so let's just get into explaining this. So right now, usually it's like if you were to do this in real life, your beaker would probably, I don't know, be that wide. And in order to standardize everything, instead of taking 1 meter gap, 1 meter is huge. So your beaker's probably not that big. So that's why they just took it as a convention to uh, measure everything in centimeters, because it's honestly more practical. And even the area is just 1 centimeter square. So this GG star value, since G star is L over A, which is 1 over meter, the inverse of so G, yeah, it's just like 1 over meter. So kappa is equal to conductance, which is ohm inverse, and this is meter inverse. But it's more practical for kappa to take the value of ohm inverse, centimeter inverse, because where you're gonna get a beaker that's probably like 10 meters wide, that's like huge resources waste. So centimeter it is. Usually I don't like centimeters, but this time it's so practical, I just have to agree with it. Okay, so now you want to find out what the unit of this thing is, because you found out unit of this. Now you just divide it by concentration. Usually concentration is what, mole per liter, because even here in this example I took 1 molar, half molar. No one takes 1 molal. Molality is kind of useless. Molarity is king over here. So you would want to convert this into, so the thing is, instead of doing all this, like ideally this is enough, but usually people are too lazy to do the conversions themselves, so they just want to look up a formula that they can use. So hypothetically, if I had in a question, if they asked me to find out this and they gave kappa value in ohm inverse, centimeter inverse, And concentration and molarity, like x molar, for example. You would have to do the unit conversions like, oh, lambda m is equal to y ohm inverse centimeter inverse divided by x mole per liter, which is y by x into this ohm inverse centimeter inverse can just remain as they are, ohm inverse centimeter inverse, and even mole can just remain as it is. But this liter, 1 liter is 1000 ml, which is 1000 cubic centimeters cc, right? So you can just write this as 1000 centimeter cube, and you get this y by x into 1000 ohm inverse centimeter inverse into centimeter cube. So that's how you would solve it. That is why the formula has a sneaky 1000 over there. I've always wondered how that 1000 popped up. But when you just do the unit conversion yourself, that 1 liter is 1000 centimeter cube, it just makes so much more sense. And another thing that I would like to discuss is how lambda, yeah, molar conductivity depends on the type of electrolyte. So hypothetically, I had like a sort of strong electrolyte, right? The strong electrolyte has a bunch of ions between these electrodes. And the thing is, right now, hypothetically, I added KCl. This has minus, this has plus. In the solution, there'll be minus minus particles right beside each other. It caused like a lot of disturbance, like these ionic attraction, repulsion, all of this. So they really feel crowded, you know. So when you dilute it, so when concentration decreases, your molar conductance increases for strong electrolyte. Example KCl. Right. And how okay, and let's say that I took the example of I don't know, like ethanoic acid, CH3COOH. This is like kind of weak. It dissociates very little into H plus. So, but you know, ions are the thing that are actually they're like the actual charge carriers. So this thing dissociates very little. So the more ions it creates, better it is. And you know, H plus concentration is kind of related to some like, I don't know, Kc or something. Honestly, I think that was like, okay. So basically, forget this. The thing is alpha. Yeah, alpha's degree of dissociation. This thing increases on dilution. So when you dilute this solution of CH3COH, you're essentially increasing the number of charge carriers. So of course your conductivity should increase. So for weak electrolyte, concentration decreases, meaning dilution increases, meaning number of charge carriers increases, which is your H plus, and number of charge carriers increases, meaning your lambda m increases. Man, if I hadn't explained this to myself, I would have been struggling right now. Anyways, see you guys later. Peace.